Okay, so far we have now covered direct map caches. We have now covered set associative caches. If you take set associativity all the way to its logical conclusion, you can get what's called a fully associative cache, where there's only a single set, and then when you're asking whether or not your block is in that set, it does a parallel compare across every single entry. So this is going to completely eliminate conflict misses, right? Because now, because you can reside in any block in that set, there's no conflict. There could be a capacity problem, but there definitely won't be an alternating sequence that will cause you a conflict miss. So in a fully associative cache example, consider one with a single set. So it has one set. It has 4 lines per set. Each one is a single byte, and it's a 4-bit address space. So derive the values for the number of address bits used for the tag, the set index, and the block offset. And then draw a diagram of this cache and a diagram of how those bits are used. So just take a minute and just repeat the exact same thing you did for the set associative cache, but this is a fully associative one. So this is what you should have gotten. There are 0 bits for the block offset, because there's only 1 byte in a block. There are 0 bits for the set index, because it's fully associative. That means the entire address is used as the tag, and you're searching every one of these blocks against that tag for your data. So that's what it looks like. There's only one set 0, and then you uniquely identify every single byte in that cache using the entire set, the entire 4 bits. So that's like a degenerate example of cache.
Would that cause a lot of extra hardware to have to be implemented?
So yeah, then you have a parallel comparison across all 4 of these.
For a single byte?
For a single byte.
But is it even faster?
It's faster in the sense that it removes conflict misses. So if conflict misses are an issue, this helps that. Okay, so let's simulate this. Here's the access pattern, 2, 6, 2, 6, 2, 6. So with 2, it's a cache miss. And because it's fully associative, let's just put it in the first one. The tag is 0010. The data is hex 22. A cache miss on 0110, but because you have space in this fully associative cache, you can put that in the next block. And then when you go back and forth, you're always hitting. So after the first 2 compulsory misses or cold misses, you get basically a 0% miss rate. Yeah.
So what do you happen once you get a full cache? You have to get rid of some data.
Then you would get, but you would have to get rid of data, but it wouldn't be because of a conflict miss. It would be because of capacity.
Yeah, sorry, that's what I meant to say.
Yep.
Like, how do you determine what is old and you don't need anymore?
Yeah, we'll get to that. In fact, yeah, later you're about 12 slides.
Yes.
Yeah. Okay, so this is what the hardware looks like if you want to do a fully associative cache, and you've got comparison circuits against every single block to match against the tag of your address. So this is prohibitive. This is why you wouldn't see a fully associative cache on a processor.
Unless it's like government, military.
Yeah, I guess maybe. I don't know.
You probably wouldn't have that used on a shield.
Well, I mean, is it a better use for your hardware, or yeah, you've got other issues? I mean, the cost-benefit thing might not actually work out in any.
You have to have custom procedure for your CPU for that sort of case.
Well, certainly so for, in fact, routers are where a lot of this sort of content addressable memory is being used. And in that case, if you're trying to keep up with line speed, you would want parallel comparisons. Because you're looking up this routing data structure. You guys have data structure. Well, there's a way of organizing data structure. And it would be nice to do a parallel compare. Like all of your algorithms are sequential. But, if you could speed it up as a partial parallel, sort of compare, then maybe you would do that. So
Especially when you do packets, because you're having to deal with a lot of packets.
In
Routing, be like, when's this going to go?
in the forwarding, yeah. So in the forwarding path, I think that's where some of this is. Okay. So now we're going to talk about overall cache design. It's sort of a higher level. So far, we looked at the cache size. We looked at the block size in terms of improving spatial locality. So the cache size, the size of a cache helps you with sort of temporal locality. If you can fit everything in that cache and you're looping around through that data, then that allows you to take advantage of temporal locality. The block size takes advantage of spatial locality. So when I bring a block in, I can hit on the rest of the bytes in that block. The associativity reduces the conflict misses in your cache so that you don't get these pathological access patterns that cause your cache to poorly perform. We're going to talk about the next three, and this is sort of a preview for your operating systems class, because these are more operating system-ish kinds of things. Because you'll see this at the operating system level, there are caches everywhere. There's the file cache, there's the page table cache, there's this TLB cache. And so the way of managing those caches has this kind of stuff built in. So the three things we're going to look at are the replacement algorithm, which you had just referred to, the write policy. When you have a write into the cache, whether or not you send that all the way out to main memory immediately, or if you wait until that block is evicted to do the write, that's what the write policy is. And then the number of caches. And so we sort of saw this when we looked at the hierarchy, but there's different ways of configuring caches in a CPU that we're going to talk about. So in terms of replacement algorithms, a replacement algorithm is needed when you have a cache line where there are no empty blocks, but you need to access some data, and you need to bring a block into memory in order to access it. And so the policy for replacing blocks in a line that's full, one of them is least recently used. Figure out the block that is the most stale in terms of access, and then you evict that one. And that's the most common one in caches. But there are others. You could evict the first one that came in. You could do a least frequently used if you're trying to count the frequency of hits to that entry, or you could do completely random. And so each one of these are valid. Since least recently used is typically the one that's implemented, we're going to go through a simulation of this and how it works. So here you have a fully associative cache that only has 2 blocks. And what you're going to do is you're going to access block A, B, A, C, B, A, B in that order. And we're going to simulate which block is allowed into memory and which one gets evicted. The LRU register says which block, 0 or 1, has been used the least recently. The one to evict, basically. Okay, so we start with A. We bring A in, and A is the least, well, you could say dash dash is the least recently used. That would be fine as well. And then when you access B, B will be brought in. Now the least recently used is A, because A has the more distant access. So that when you bring in, when you access A, it's going to hit, and the only thing that's going to change is the fact that now B is the least recently used. And when you access C, now C needs to replace either A or B, and because B was the least recently used, it replaces B. But now your least recently used is A, so you have to update that. And this is what the cache is doing as well, in order to manage its policy. Then B is brought in to replace A, and now C is the least recently used. And then when A is brought in, C gets replaced, and B is the least recently used, etc. Yeah.
So it actually has a counter checking to see how many times this happens, or like which one's was hit last.
It has a state
Or
machine.
not.
I don't know if it's a counter. Might be a counter. Some sort of state machine to figure out which one is the least recently used. Yeah. Okay. I will simulate this. So here is an access pattern. Again, the same main memory as we've always had. We have a two-way set associative cache. So there are two sets, 0 and 1. Each set has 2 lines in it. This is our access pattern. Each block has a single byte, so there are no block offset bits here. So the set is the least significant bit as a result. So all of these are going to hit in set 0. And so here's the simulation, 0010, that's brought in. And then hex 22 is stored. 0110 gives you hex 66 in the cache. Now hex 22 is the least recently used. But when I access that, now hex 66 is least recently used, and this is a hit. When I access all zeros, then I'm going to have to replace the least recently used, which is the other block. And now the hex 22 is the least recently used. So, but I access it again, so that's a hit. And now the other one is least recently used, and so when that misses, I replace the one on the right. Does that make sense, how that operates? Okay, the next design decision is the write policy. So the idea here is what happens when data is written to memory through the cache. There are 2 cases for these policies. One is if it's a write hit, meaning the cache, the block was already in the cache, so it hit in the cache, and you're trying to modify that piece of data. The other case is a write miss, where the block that you're trying to write to is not in the cache. Okay, so those are the 2 cases. So we're going to cover the first case, for the write hit policy. So what happens if the data is in the cache and you try and update it? The 2 kinds of caches are the write through and the write back. The write through says if you have a write and it's updating something in your cache, send it all the way out to main memory. Just completely update it everywhere, because otherwise you'll have a stale version in the cache, or no, stale version in main memory versus what's in the cache. Okay. This is helpful if you have a multiprocessor setup, and the processes on these processors are sharing data. Like they've mapped shared memory together, in which case if one person updates the memory, you want that to be immediately updated on that other core or the other processor. And with the write-through cache, basically the other cores can continuously monitor the main memory traffic for that write that goes all the way through to main memory. And when it sees that piece of data being written, it can automatically update its own cache. So this is called cache coherency, which will be an operating system thing when you look at how multiprocessors work. Cache coherency is one of the things that you might like in a multiprocessor. But again, this doesn't come for free. Nothing comes for free. This is a lot of traffic into your memory subsystem, and it slows down writes because you have to wait for the whole thing to commit. The write back policy initially only updates the cache. And then what it does is that it marks a bit. They call it the dirty bit. They mark that so that if it needs to get replaced and the dirty bit is set, then you write the whole thing out into memory. So you only update the main memory if it's been modified, basically. Okay. The draw, yeah.
So can you go through write back again? So you write it to the cache and then update a dirty bit in the cache or in memory?
In the cache.
Okay.
So then in the cache, that line gets marked as modified.
Modified.
And then when you have a replacement algorithm, eventually it'll get evicted. when you have that replacement algorithm, the replacement algorithm will see that the dirty bit has been set, then it actually has to commit that change into memory.
Okay.
That's what it's doing. Yeah.
It seems kind of dangerous though, because then you could have like if you can look at if you can set any of that inside of somebody else's cache and then write a little bit of information that you could update people's values on. It seems like that could result in security flaws.
Sharing a cache does result into security issues, or even sharing memory, or sharing the machines in the cloud. All of these have side channels and ways of getting at someone else's stuff. So yeah, it's not unique to this though.
Yeah.
This particular thing. The only issue with this is that now your main memory is out of sync with what you have just updated your program state to be. And if you're using shared memory, that means you have out of sync copies of data, right? So routing tables are an example of this. You might have one process doing the forwarding, the other process calculating the routing table and updating the forwarding table. So that may be a bad one. But if you have multiple ones that are trying to lock a particular piece of data and or trying to get an update on a particular piece of data, then that results in a problem where your data is out of sync. Okay. The other kind of policy is a write-miss policy. And this policy is when you have a write into memory that's not in the cache. Then what do? The two things you can do is allocate a cache line for that write. So you bring it into memory, into cache. You go to memory on the miss, and you bring that line into the cache, and then you modify it in place. That's write allocate. So you load it into the cache. The other one is to just write this to main memory, bypass the cache, and don't load it in. So this you would do if you expect to, after you have written that piece of data, if you expect to read it again. This is if you're writing stuff out to memory and you don't expect to read it ever again, then you would do this policy.
The first one actually will write it into memory, then pull it in, or
nope, it won't even pull it in. The second one. So the first one will pull it in and then modify it in memory. But we're not talking about write hit yet. So whether or not it gets committed to both memory and cache, that's sort of what the write hit policy is going to be. You're going to couple these things together. But yeah. Okay, in fact, that's what this is right here. So typically, what you do, a write-through policy is paired with a no write allocate. But if you do a write-back policy, you pair that with a write allocate policy. So that's typically how they're coupled together, which I think sort of addresses what you were talking about. Okay, the last part is the number of caches that you have. So as both the logic density increases and the memory gap, the CPU memory gap widens, we've basically kept, you've seen that we've gotten these deeper multi-level caches. So both on-chip and off-chip caches. And so we saw previously that the hierarchy, as we've gone on, has deepened with starting from the Pentium 2, which only had a single L1 cache on chip, and then L2 was off chip, all the way to the Intel Core, where there's an L1 cache and an L2 cache per core that's on chip. Then we have a unified on-chip cache, L3, and then we have the L4 is being off chip. So now we've gotten these multiple levels. So that's one way to increase the number of caches on your CPU. Another way is to split caches based on what they store. Have separate caches for, in particular, data sort of locations and instruction locations. So the advantage of this is that now your instruction fetching, the caching of the instructions coming into memory or coming into the CPU are decoupled from your data access. So you hopefully get a better hit rate for both. They're not thrashing with each other, is basically the idea. The disadvantage is complexity, because now you have to have multiple pathways of doing the caching, one for data and one for instructions. Okay, so the cache parameters are exposed using the CPU ID x86 instruction, which there was a program earlier that had it for whether or not you had MMX. It's the same instruction. CPU ID will load up all your registers with everything that it supports, and one of the things that it gets sent back is your caching information. And you can get programmatic access to it if you run this command. Do a get comp-a, and in fact, for your last homework, you're going to be running this Memory Mountain program. On the machines that you do this for, run this command and make sure that what you're getting back as a result matches up with the sizes of each one of these caches in the get comp. You can either do it on Linux, you can either do this command or this grep command to figure out the size of your L1 caches. So there's an L1 data, L1 instruction cache. There's an L2 unified cache. And then these you don't care about, but you should at least be able to see that when you run that homework assignment, that you can get something similar to this. You can see where the drop-offs are. Okay. Yep.
Did you provide the Memory Mountain
It's
program, or did you want us to like?
You can either get it from the book's website, or I have it. I believe I have a copy of that linked. But if you need it, if you can't find it, let me know. Yeah, and this assignment is just a simple finding 3 or 4 systems to run this thing on, or I think it says 3, and then just hopefully different systems. So find some really old systems, and then find some newer ones like maybe Linux.cs or.
Try different architectures.
It'd be great if you could do like Lab 1 and then just the regular CS SSH, right? Since they're such different. Like we've got the i7s in the lab, and then we've got, if you don't do the lab ones, then you're gonna get some.
Do your laptop,
yeah.
and then if you can get it running on that, it's not a window. So these are Linux binaries.
That's right.
You could compile if you can. The program doesn't use anything. I mean, specifically Linux, so you could actually compile using Cygwin or using Visual Studio, and then just run it. Yeah.
I don't know if the performance of it, because we've got 2 different operating systems which may have a bunch of different.
It's running a very tight loop that's not going to be context switched out typically. So the other thing you can do, you could even install a virtual machine on any one of these things, and then it should still work because it'll run. As long as it's running in a loop that's not calling into the operating system, it should eventually own the entire cache. And then it might get swapped off here and there, but it should work. Okay, so actually that's what I'm going to talk about now. The Memory Mountain program. This is what your final homework is, and it shouldn't take you very long to run it. It's to get a copy of this program, run it on a bunch of systems, and try and figure out if you can regenerate what I'm going to show you is as a sample for this. So what we're going to do is we have this program that measures the read throughput through memory of your machine. And so it's going to try and figure out how many bytes per second can I pull in from memory. And so I want to tweak 2 things. And the 2 things I'm going to tweak is the size of the data set. And so if it's too big, it won't fit into the cache, and then you'll lose temporal locality. So here's how we're going to measure sort of our temporal locality, and it's going to be based on the size of the data set we're going to access. The other one we're going to look for is spatial locality, and we're going to try and figure out what is the block size of the cache. And the way we're going to do it is we're going to change the stride length. The stride length is going to start with a length of 1, meaning I'm going to get elements 1 at a time. If it's a stride length of 2, I'm going to go every other element. If it's a stride length of 3, I'm going to go every third. And you can see if you get every nth element, you start to impact the spatial locality that you see. So if the stride length is 16, and you have a cache line that's 16 elements long, then you get no spatial locality because you just hopped over the entire data that you brought in along with that original data. So that's what we're going to look at. So
So what are you gonna find? So what are you gonna look for specifically when you run this? Like, is the performance gonna fall off?
It's gonna fall off, and it's gonna fall off in a very specific way, which is why this is called a mountain. It's gonna look like a mountain, and the mountain, the tip of the mountain, is when you have a very tiny data set, a tiny array, and you're accessing it in a stride 1 pattern. That is your optimal throughput. And then all the way on the other side, the valley, is when you have an extremely large data set array, and you're going every 16th or every 32nd or every 64th element in that array.
So at the peak is what your cache size would be?
It's well within your cache size. Yeah, the peak area is everything fits in L1. And you're accessing it in a stride 1 pattern. That's the peak of the mountain. Okay. This is the code. And we don't have you write this code, although Mark Morrissey on the instructor in the other section, he's like, yeah, I'm going to make them write it next time. So be fortunate. I'm not going to make you write it, but I do want you to understand what this code is doing, because at the highest level, it's really easy to sort of figure out what it does. The two things that you're going to parameterize are the number of elements to loop over, so that changes your working set size, and the stride length at which you're trying to read data from this array. So you'll start with this enormous data array that's got this max number of elements, and these are longs. Oh no, those should be ints. No, those are longs, sorry. So, and then what you're going to do is you're going to say, hey, I'm going to vary the number of elements that I'm going to read out of this data array, and the stride length at which I'm trying to read it from. And that's what this is. So these stride lengths, as you increase the stride length, you're going to basically get the 2ith element, the 3ith element, and the 4ith element. So you're basically increasing the gaps between successive reads. And so this is your read loop. And so you can see you're going to get the 0th one, the 0 plus stride 1, the 0 plus 2 times stride 1, the 0 plus 3 times stride 1. So that is going to give you your spatial locality. As you increase the stride, you'll see that these data accesses become more distant. What I'm also going to do is change the number of elements. So you see this length parameter is set to the number of elements. And the limit, so I'm taking these 4 at a time, so basically loop unrolling. So the limit is associated with the length. And then basically what I'm going to do is I'm going to loop until the limit is reached throughout this data accumulation. And then I'll basically repeat this test loop over and over again. So do you see how this test function is going to basically give you control over the working set size and how you're accessing the data in that? Then we're going to time this. Right? And we're going to time this and then normalize based on the amount of bytes. Or we're going to figure out how many bytes per cycle I can pull out of this loop. And each iteration of this, based on the elements in the stride, is going to give me a different bandwidth. So that's what this memory mountain. The memory mountain program wraps its stuff around this test function. But this test function is where it's at, where all the real logic is.
Just let you know, after a quick look over the fangs of each one.
All right.
I didn't know how you wanted us to do the timing and everything.
All right. The memory mountain does the memory mountain will spit out a megabits per second, basically. Yeah, you're not doing any of the timing, but you can look at their code to see how they do the timing. That's fine. So this is their result. So this is the mountain, and we said the peak of the mountain is stride 1 access on a small data set. So that's here. The data set is, the size of the working set is on this axis. The stride length is on this axis. So stride length of 1 all the way up to 12. And then this is the read throughput is on the z-axis. And so you see stride length of 1, small working set size gives you the highest bandwidth. The features of this, along this cut, you see different plateaus. And these are ridges of temporal locality, because as your working set size increases, you are then going down to slower and slower sort of parts of the memory hierarchy. So that impacts your temporal locality. And then across this cut, you see these slopes of spatial locality. And these things will linearly decrease based on the stride length. So for example, when you go from stride length 1 to stride length 2, you're going to have the bandwidth, right? Because you're basically having the hit rate. So that's why you get this linear drop-off. And then eventually, when your stride length is beyond the length of the cache line, this will eventually plateau here. So the next couple slides give you these cuts. It cuts one part of it or the other. This one cuts the first one, where it's the temporal locality one. And as you increase the working set size from right to left, you see that you you go from one plateau and you drop down to the next. And so by looking at where these plateaus are, you can figure out that this is my transition point from the L1 cache into the L2 region. And from the L2 region to the L3 region. So you can sort of see that maybe the L2 cache might be 256 kilobytes, and then the L3 looks like around 6 or 8 megabytes. Yeah.
How do you tell that the L2 starts at right after 256 and not right before it?
Oh, you're right.
Because that's the way I would.
Maybe it's a 128. Well, so the other thing is right at the edge, you have other code that's in there that might be competing, so that might be, yeah, that might be why it drops early. Exactly,
like,
yeah.
Reading it and
You're right, though. That looks like a drop off at 128 kilobytes.
mm-hmm.
Yeah, all right. Yeah, don't know.
I mean, you just test whatever your processor you're using, right? Just look at it's got an ivory bridge. It's this.
Yeah, that's probably what they did.
Yeah.
But yeah, in fact, when you run yours, you might get something similarly noisy. It depends on what else is on there. If you run it on a Linux system, there's this command called renice, which tries to give your priority access to the CPU. I don't know if cat lets you run that command.
Probably not. Because that'd be very.
But if you can,
It's called renice.
renice. Or actually, when you invoke the command, you can just type nice and then the command, but you give it nice -19 or something. I think it's negative numbers higher priority. And then try and get it so that your thing runs at the highest priority, so that it might not get swapped out.
Yeah, negative numbers are higher. Yeah, because I just did that capture the flag.
The PS.
Yeah.
That's PS. Oh, yeah. So the PS. Actually, yeah. If you do that level, then you'll know whether it's negative 19 or positive 19.
Oh, the PS signal.
The PS signals one.
That was fun, but really weird.
All right, so the other one is slopes of spatial locality. And so as you go increasing in stride length, you'll see this drop-off, this linear drop-off in terms of hit rate, because now every nth one is being returned. And then eventually this will plateau, and this is going to plateau at 1 access per line. And it won't get any better. It won't get any worse than 1 access per line. So that's what I want you to do for your homework, is to test this on a bunch of systems. Okay.
Do you want us to do the write-up in any particular manner?
So what do we turn in for this?
I believe it is described in the assignment. I think it's just the output of the runs in the homework. So it's basically out of the book, I believe.
Because the website just says, it's this problem in the book, go do it.
Yeah, so basically the book is going to ask you to do certain things. You just, give the output of that is basically what we want.
Over the string, the extra credit meta CTFs today?
No, it'll be during finals, during the last week of next week. So, okay, so I did release the extra credit meta CTF levels if you want to do it. It helps if you watch the 2 lectures, and those are added to the channel. And what I would do is watch the short one first, so you know what you're doing. And then the second one is actually a walkthrough of the levels as I do them. So you could either parrot the process that I'm using, or you could try solving them on your own. I recommend trying them for like an hour or two. Well, I don't know if you have an hour. Sorry. Just try them and see if you can start knocking them off in sequence. That's the preferred way of doing it. You'll feel better about yourself if you do that rather than parrot what I do. But yeah, I don't know whether or not it's doable. So I think it's doable from what you know right now. You should be able to do those without too much difficulty, I think. But if you do run into difficulty, then that walkthrough, the format lab walkthrough, I go through every single level. And I think I solve it live. But obviously, because each one of you have different binaries than me, you still would have to repeat that using your own binaries to get the answer.
Can't you just wait to watch your answer and just plug it
You can't just plug in my answer. Yeah, it won't work. And if it does work, then I need to know that, because then those things got...
Of course, after
Yeah.
we test it for all 8 of them,
Yeah.
just to make sure they it's all
And to be honest, so all of those levels were developed by a single student over the summer. So that's basically what I do is, like, if people have interest in developing levels for this thing, yeah. And so if you look at the way the thing is scaffolded, it's quite brilliant actually. Where they can, this person was able to get levels that target very specific things in that vulnerability. So that's why I offer it. It's a good sequence. Did you pay $1? Oh, no. No. Well, he got a stipend. Yeah, actually, yeah. I paid $3,000 for that sequence of levels. Yeah, there you go. I paid.
I would not design levels.
I'm going to work on that.
You
Yeah.
have to pay me more than $1.
Yeah, I don't know how he didn't spend that much time on that, but I did. I don't know what that works out to, but yeah. All right. Actually, or I've been getting my students as final projects to do levels. That's some of these that you did this time around were projects. All right, so where the rubber hits the road with caching, where it really matters, is when you're writing programs. So that is what we're going to cover next, and we're going to use the matrix multiplication example. So if you recall, if you have an n by n matrix, matrix A, when you multiply it with matrix B, the result goes to matrix C, and what you're going to do is you're going to take rows of A, columns of B, you're going to do the dot product, and that's going to set a single value in the result C. And then you're going to do it for all the values of I and K. So this is the loop. For I, J, and K, you're going to go through and sequence through these arrays. I'll show you visually the way it's done. But when you want to multiply an n by n matrix, this is an order of n cubed number of operations. For each element, you have n reads per source element as you go through this n by n computation. And then n values are summed per destination. So the two things that we want to consider are the cache size. How can these matrices be fit into the cache? And then the block size. Can we exploit the spatial locality of the line size to improve our hit rates? Okay, so the canonical sort of implementation of the matrix multiply is what we're going to analyze. And so we're going to assume that we have double precision floating point numbers in this analysis, that the line size is 32 bytes, meaning that you can fit 4 of those doubles in that single line. The matrix dimension n is really large, so you're not going to be able to fit the full matrix into cache. And then what we're going to do is we're going to look at the axis pattern of the inner loop. So what I have shown you are rows of A being multiplied by columns of J, and then producing the individual elements of C. So in order to go through this example, I need to refresh your memory about how matrices are stored in memory. So they're stored in row major order. So the elements along a row are stored contiguously. So when you step through columns of that row, you get successive elements, and this is good for your spatial locality. Likewise, if you go through rows of a single column, you're basically skipping elements. And if the row is really large, which in this case they are, you're going to get no spatial locality on axes that go down a column. Okay, so in this case, if you have something like this, where you're sequencing through columns, through a rows in a single column, you get a 100% miss rate. So those are the two things. So here you'll get a non-zero hit rate, but then here you'll get a 0 hit rate. Okay. So this is a visual of the computation as we know how to do it. This is the computation that they show you in math class in linear algebra. You guys have all taken linear algebra? No, you don't
Next
have.
term.
Next term?
It's all right. Took it like 9 years.
9 years ago. Okay, so you take.
I did that last term.
So this is taking at least the way I learned it is that you take a row of A, and then you take this column of B. So the ith row of A, you take the dot product between that and the jth column of B, and that will produce C of ij. And then you loop through all of the rows of A and the columns of B, basically. All the different combinations. And that you update the sum. So what is the miss rate per inner loop iteration for this? Given what we have just talked about. You have
For K or
for this inner loop. Like how many misses would you get for a single iteration, for the single one? For a single, so actually, yeah, for the single loop. There'll be a lot, but as a percentage. As a percentage is what I'm looking at.
Doesn't this all depend on what the cache size is? If it can store all, like how much it can store?
This is independent of the cache size, actually.
you're gonna miss every single time because of the BK.
Yeah.
So this is going to miss every single time. What about this one? So we said these are double floats, and then each cache line can fit 4 floats, 4 of these double floats. So what would be the miss rate on this guy?
How wide is
1
it?
and 4.
How wide is it?
It would be miss every 1/4.
So 25% miss rate. Okay, good. So for A, 25% of the time it will miss, but then because it brings in the 3 other doubles, then the next 3 iterations after the miss will hit on this one. This one is always going to miss, no matter what, because it's going down the column. Okay.
Is there a way to flip your matrix in memory and load in a different set of your memory to make it so you don't get that miss all the time?
Well, you can use the transposition of the matrix part, I think. You can use the transposition of the matrix, but then you've got to do all the operations to do that.
But that's
I like the way you're thinking because you're looking at reorganizing this computation because of what you know in the underlying computer architecture.
Yeah.
That's what I'm teaching. That's exactly what you're supposed to get out of this. So yeah, this sort of sucks, right? I get a complete miss, like no matter what I do on this column. So, and you know, this is okay. I want to keep this. I want to keep this and try and do better on that, but I don't know if I can. But there are ways of reorganizing this matrix computation, assuming commutativity and associativity and these sorts of things, and
well, unrolling too.
All you have to do is find the transposition of the matrix and just flip the columns and the rows, but that's going to require you to spend a bunch of operations to do that. Restructure.
we don't want to do that, but we do want to organize our computation.
But multiply or instead of multiplying the column, you'd be multiplying the rows, which would be a little weird, but.
Yeah, there's a lot of weirdness going on here eventually. But so this is one way to do it, right? I have the row of I, the column of the row I of A, the column J of B, and then I do this inner loop that sequences through these elements and these elements. One variation I could do is to swap J and I. We've seen this before, but this is going to do the exact same thing, right? This inner loop doesn't really change. But another thing I can do is this. I can fix an element of A, and then I can go through that row of B, updating the row of C with the incremental deltas that are associated with this ik and A, combined with this vector, this row of B. You see what that does?
It turns into fourth.
So you're reorganizing the computation. Eventually, when you go through all of the elements of A, you will end up with the exact same result. But rather than calculating an element of C in its entirety all at once, you're updating C. You're fixing A and updating C instead. And this is equivalent. This will give you the exact same result. So let's look at the miss rate per inner loop iteration.
But this won't change the big O notation of it.
It won't.
Still.
Yeah, it'll be the same. Still n cubed. So what's the miss rate for this one?
Oh.
Yeah, a quarter. What's the miss rate for that one? 0.25. Does that seem better?
Yes.
The one issue here is that in this one, you have this sum. So it's not all roses on the second implementation. You have this, which can be stored in a register. You have two reads, and then a single register update. If you look at this implementation, you have two reads, the B and the C, but then you have an update back into C. So technically, you have more memory operations. One has two reads, the other one has two reads and a write. So does that come out in the wash? Is that okay? Well, if you look at the microarchitecture, how many loads and stores could we do in our execution unit, if anyone remembers that?
2 loads and what was the other one you asked?
2 loads and 1 store, if you remember. So actually, this might actually be okay. And you can issue a 1 per cycle on both of those. It just has a certain latency. But when you talk about an inner loop, you could actually keep up using 2 reads and a store, potentially.
Well, and you could unroll it too a little bit.
You could unroll it as well, yeah. That's for sure. Okay, so this is better read performance, but now you incur a memory store per iteration. But that might beat a cache miss. And then we'll find out when we run the numbers. Okay, you could do, so this was Kij, you could flip the top 2 and get Ikj, which is going to be the same. Here is another way of implementing this. You could do columns of A. You could fix the element in B and use a column of A to update a column of C. And I gave you, this is terrible, right?
Yeah,
But still, you might as well try it out and see if you get something that's logical, right? This is a deterministic miss on both C and A to read, and you incur a write. So for sure, this should give us the worst performance. Likewise, if you permute the J and the K, you should get the same thing.
I was really afraid it's going to somehow magically be better.
Yeah.
I was like, wait.
Yeah, so this is the summary. So these are the candidates. Matrix multiplication cage match. We have IJK, KIJ, and JKI, and these are the loop iterations. So 2 loads, 0 stores, 2 loads in a store, but the number of misses is 0.5, whereas the misses per iteration here is 1.25. And then JKI, which 2 loads, a store, and 2 misses per iteration. That should definitely lose. And so this is what you get. This is the cycles per loop iteration. So we want lower. The big square, and sorry you can barely see this, this is our pathologic KJI, JKI. So yeah, this is guaranteed the worst performance. The one in the middle is our first one. This is IJK and JIK. And then the one at the bottom that gives you the best performance is the one with 2 loads in a store, but 0.5 in terms of the number of misses per iteration.
So the obligatory will a compiler actually compile it to not do the bad one?
You could try that out. Yeah.
It should never, because that would change. That's fundamentally changing the structure of the program, right? They wouldn't be able to do that. So it treats its inner loop as a function, and then so it can rearrange the stuff inside the loop, but it can't do anything outside of that loop, can it?
This is all within the same function, but then the other thing is floating point operations are technically not commutative or associative, so the order does matter. Not clear. I actually don't know, but that's something that's easy to check, perhaps. Don't know, actually. Okay, so the matrix multiplication, it takes advantage of the spatial locality. But the size of the matrix really makes leveraging temporal locality difficult. If you look at this, eventually, not that one, this row eventually will get cached out, right? Like there's no way to store both matrix B and matrix C all into the cache memory so that eventually you can get 100% hit rates going through your cache. Eventually, this line, after it gets updated, is going to get evicted on the next outer loop, is basically the issue. So we don't want that. So one of the ways, so you use your knowledge of the matrix computation, and this is what you would do if you're trying to optimize performance using any scientific computation. You try and reorganize your computation into smaller blocks. And so just like we reorganized our computation to incrementally update the result, you can do so at a block level on the matrix multiply. So the idea of blocking is to take subsets of the matrix, like A11, A12, A21, and A22, and operate the matrix multiply on subblocks of matrix A, B, and C, and then update within those blocks continuously. Then you can fit the subblocks into memory, do all the operations you need on that with that subblock, updating the values that you need, and then go to the next subblock. In which case, then yes, you can get more, you can get better cache hit rates through there. So that's the overall idea of blocking. And so I don't want to take you through the details of it, but I just want you to conceptually see that if I focus on subblocks of A, B, and C, and I figure out how to update from those, I can fit myself into the cache, and then I win. Okay, so this is the implementation of it. This is visually what you're doing. You're taking small pieces of this, and then updating this part of this row, this tiny part of C, using these two blocks, and then continually going through these tiny rows of A, using this as B, updating that part of C. So this is your final answer. So this is where our best one on the previous slide, and then you can get even better cycles per duration using that final one.
110. That's
Yeah.
crazy.
Okay, so that is caching. That's the memory chapter. Questions? I think we have some time too, right? 3:35. That's like a new record. I'm gonna stop there. And actually, the next couple of lectures will be shorter. So yeah, more time for questions, problems you're having.
I did have a question on the loop unroll.
Mm-hmm.
Since we have time.
Yep.
The loop unroll, CTF. I went through and I did the math